Okay, so this is our first try at a remote classroom. So my goal today is to practice with the concepts which you've studied. I am assuming you've studied deeply and summarized the main ideas from the reading from chapter 8, sections 1 through 3. And we're going to jump into applying those concepts to concept questions 1, 2, 3, 4, and 7, and then exercises 2, 7, and 16. Okay, now as we proceed, I'm gonna pause and invite you to stop the video, and it's imperative that you do so, that you really try and struggle with these as much as you can before looking at my hints and my solutions, so that you can really make progress with internalizing the concepts and the techniques. Okay, so you could go and just take those problems right now and try and go solve all of them right now. That'd be great. I'm going to go through just one at a time, and just give kind of hints about how to proceed, and I'll try and do it as efficiently, clearly, but also quickly as possible to keep the video a manageable size. Okay, so first one, concept question 1. Go read it, pause the video, try to solve it as best you can before coming back. Alright, so the question is, what is uniform circular motion? So we have uniform circular motion. What is constant in uniform circular motion? Okay, so first of all, what does uniform mean? Uniform means it's going at the same speed. So speed is obviously constant. So uniform means the speed is constant. Okay, now what does circular mean? Circular means it goes along a circle, which means the direction is constantly changing. So is velocity constant? The answer is no. But why is it not constant? Speed is the magnitude of velocity, but velocity carries direction. And since it's constantly changing direction by going in a circle, the velocity is not constant, only its magnitude, which is the speed. Okay, so not velocity. Alright, what about angular velocity? Angular velocity is a little bit different. Angular velocity has a constant, for uniform motion, it also has a constant magnitude, but also is a vector, but its vector always points along the axis of rotation. So if you're going around in a horizontal plane, then the angular velocity points up or down. And if you're going at a constant speed, then that never changes, just up or down. And so angular velocity is also constant. Okay, well, what about centripetal acceleration? What does centripetal acceleration depend on? Okay, we found earlier that centripetal acceleration has a really, I guess I'll write it down here. Centripetal acceleration has a really important relationship to the tangential speed, v squared over r, where that velocity is the tangential speed, or that vt is the tangential speed. And we just found that that's constant, and the radius is constant, so the centripetal acceleration is constant in magnitude. But the question is, well, isn't it a vector? It points along the radial direction. And that's constantly changing. If it could be pointing left, right, up, down. As you're going around the circle, it's always pointing towards the center. Well, technically, it just depends on your coordinate system. But we generally, for circular motion, choose a coordinate system that has a radial component and a tangential component. So our coordinate system moves around the circle. And so the acceleration always points inward, which is always along the radial component. And so it is constant. So the centripetal acceleration. Okay. Now what about the magnitude of the net force? What does it depend on? So Newton's second law is the big connection here. Newton's second law, it relates forces to accelerations, and if it's uniform circular motion, that means the only acceleration is the direction changing one, or the centripetal acceleration, and so the net force points in that direction, that radial direction, and is equal to mass times that centrifugal acceleration, which we just argued was constant, therefore it's constant too. So all of those choices are constant except for velocity for uniform circular motion. Okay, so on to question 2. So pause the video and go try and solve 2 on your own. Okay, in this picture we have a car that is traveling through the bottom of a circular valley. Okay, and it runs out of gas, which means it's just coasting. There's no tangential acceleration, no power that's pushing it along its path. So the only acceleration that's possible is the radial acceleration because of the direction change. Okay, so with that in mind, what is the net force diagram? What's the free body diagram look for this? Okay, first of all, if there's no power moving it forward or back, okay, we're neglecting drag or rolling friction. It means there should only be 2 vectors, an upward and a downward vector. The normal force of the road pushing up on the car, and the gravitational force of the earth pulling down on the car. So that eliminates D, E, and F. Okay, so the final thing is, well, what's the net force on the car? And that's determined by the direction of the acceleration. So I ask, what is the direction of the acceleration on the car at this point? Now the direction point, it's going through a circle, circular motion, and the direction changing, or the centripetal acceleration, always points towards the center of the circle. So in this case, at the bottom, the center of the circle is somewhere up here, so the acceleration must be pointing up. So if the acceleration is up, okay, that means the net force must be up by Newton's second law, which means on our free body diagram, we better have a bigger upward normal force than the downward force of gravity. Okay, so that would be choice A. So the normal force must be bigger than the force of gravity because the acceleration is pointing up, causing an upward net force. Okay, we're going to see this idea applied a lot. We have to be very careful to remember that in circular motion, we know the direction of the acceleration. We know that at least, even if it's speeding up or slowing down, we know that for circular motion there is a component of acceleration that points towards the center of the circle. No matter where on the circle, it always points to the center. So in this case, the acceleration points upward, meaning the normal force, which points upward, must be bigger than the downward force of gravity. Okay. Let's move on to number 3. Go ahead and solve number 3. Okay, so number 3, how'd the rankings go? Well, the question is, what is the tension in the string? Rank the tensions in the string. So the main idea is what? Well, it's what is the relationship between tension and radius, velocity, and mass. Okay, well, that comes through Newton's second law. The tension is the only force acting on it, and it's pulling towards the center in the same direction as the radial acceleration, or that centrifugal acceleration, but we know that that acceleration has a special value. Okay. The tangential velocity over the radius. So the tension is proportional to these. So in the given variables for the problem, TA is going to be equal to m, and then they just use a v squared over little r. Those are the variables given in the problem. Well, what's TB? TB is the same mass, same velocity, but twice r. Okay, so it's half as big. The tension in case B is half as much as A. Well, go ahead and continue with C and D. What do you get? Okay, so continuing TC, it's double the mass, so the same velocity and same radius as A, so that's twice as big as A. And lastly, TD is double the mass, same velocity, but double the radius, and so that's the same size as A. So C is the biggest, B is the smallest, A and D are equal to each other in the middle. Alright, let's look at 4. Go ahead and look at problem 4. Try and solve it. Okay, so here we have Tarzan swinging on a vine and is currently at the bottom of the swing. So Tarzan is swinging through a circular arc. And at that point, is the tension in the vine greater than, less than, or equal to the force of gravity on Tarzan? Okay. How is this problem different than this problem? How is 4 different than 2? Okay, I hope you're able to see that it's the same problem. The car is being pushed upward in this circular motion by the normal force. Tarzan is being pulled upward in a circular motion by the tension in the vine. Gravity is pulling down on both of them. And so in either case, this diagram looks the same, except instead of a normal force, it's tension. So the tension must be bigger than the gravitational force. Okay. So this is a really good example of seeing the similarities. We're using the same process to think about it and seeing that these are basically the same problem we've been able to analyze. Alright, now let's move on to 7. Go look at 7, see what you can do with 7. Oh, hold on, I apologize. I wanted to skip 7. I'm not going to do 7. Okay. So, now let's move on to exercise 2. Okay, we're going to do exercise 2. Go ahead and look at exercise 2 and see what you can do with that. Okay, this is a fairly complicated problem in some regards. It's actually just two-dimensional motion, and we have to take a little bit of extra care to use forces to figure that one out. So if we think about it, it's really good. This would be an example of a really important one to do a full picture. We have this cart, okay, that's moving with some initial velocity, v sub x, okay, and on this cart we have a rocket that provides an upward force. Call that F thrust. Okay? And at t equals 0 it launches, and we're trying to make it get through a hole over here, some distance x away, which is our x-axis. Okay? We know that it is a distance y above, and we need to know when to launch these engines, this rocket engine, so that it can fly up there. Okay. Now this is very much like a projectile motion problem, only kind of in reverse. There is an upward force rather than a downward force. I mean, there is a downward force of gravity, but there's a dominating upward force. So there's a net upward force that allows it to accelerate upwards. So we get projectile motion, but it's going to be kind of an arch like that. The sideways motion is constant, just like we'd have normally. And now we have this upward motion. So this is really just a projectile motion problem, only we have to find out the acceleration in the y based on our knowledge of the net force acting on this rocket. So that's where a free body diagram would be good to analyze this rocket. Go ahead and try that. Okay, so if you look at a free body diagram on that, we have this downward force of gravity on the rocket, but we have a big upward force from thrust, this upward thrust force, okay, giving us a net force upward. And that is going to be equal to MAY, because it's only in the upward direction. So what is our F net? Well, we have F thrust, which is a number that we're given. Subtract mg, subtracting that downward force, gives us this upward acceleration times the mass. And so by using this, we can solve for a y. And then it's just now a two-dimensional kinematics problem. We can figure out how long it's going to take to get up here. Okay, to find the time it'll take to get up here, because we know how high it is, and now we know the acceleration in the y. We can find out the time, knowing it starts from rest. And then the horizontal motion is just constant velocity, and so we can then solve for that one. I'm going to let you follow that, since the main idea was using our net force to find our acceleration and then recognizing how to break it up into components. But I'll give you a clue that using the y component, the time ends up being 2.54 seconds. So you can get that from the y component of the motion. Again, finding a y first. And then using that in the x component, we can get that the distance you'd have to travel, if you assume you start at 0, so x1, is going to be 7.6 meters. Okay. Now noting that the y distance is given, the y distance is 20 meters, but these numbers seem reasonable. Take for something that's accelerating at a decent clip, about 2.54 seconds to go 20 meters for a little model rocket seems reasonable, and a horizontal distance of 7.6 seems reasonable, since it's going to curve quickly upward. Okay, so that's number 2. Well, let's do number 7 now. Okay, go and look at number 7 and see what you can do with number 7. Okay, so number 7 is a block, a 200-gram block, is on a 50 centimeter long string and swinging in a circle on a horizontal frictionless table. Okay, so this is not a vertical circle where we have to worry about gravity acting on it. It's a horizontal circle moving around. Okay, so with that, what is the speed of the block if it's moving around at 75 RPM? So that doesn't need anything about circular motion except just a conversion. We have V is already given as 75 RPM, or revolutions per minute, and we just simply have to convert that. Okay, 1 revolution is 2 pi r meters. Okay, and then because that's the circumference, 1 revolution equals 1 circumference, so that's 2 pi r in meters. And then 1 minute is 60 seconds. So doing that, we get the velocity in terms of meters per second. That's 3.927 meters per second. Okay, so that one is just a conversion. Alright, now with that velocity, okay, we want to find the tension in the string. So how does that velocity help us find tension? What is the missing piece there? So the missing piece is acceleration. That is so critical. Newton's second law relates the force to the acceleration, and in this case this is a tension pulling inward. It's pulling along the string, which is radial, giving us our radial acceleration. And we know that the acceleration is the tangential speed squared over the radius of the curve. Okay, now we just found this tangential speed. This is the tangential speed, meters per second. And we know the length of this string. That gives us our radius. We know the mass of the block. And so we can find the tension. So this is this problem ends up being fairly simple because we can reduce it using Newton's second law and this critical relationship between tangential speed and the centrifugal acceleration. So just plugging in our numbers, we end up with 6.2 newtons for that one. Okay, well, that was number 7. And so let's move on to problem 16. Go ahead and look at problem 16. Alright. So problem 16 is about circular orbits. Now there's something really cool about circular orbits, and so I'm going to kind of give a little bit of a conceptual overview and see if that's enough for you to solve problem 16. The text, which I'm sure you read, says that the velocity of an orbit is equal to the square root of the radius of the orbit times g. Okay? That's useful to write down and to have, but you need to be really careful with that. And it's so easy to derive from fundamental principles that I'm going to require you to do that. Because I want you to think about where that came from and how to adapt it to different things. So think about where that came from. Let's take a picture of this problem. We've got some planet here, and we've got a moon. Let's go and take this to be the Earth and a low orbiting satellite. Okay, before we get to the problem in this exercise. Okay, now if it's a low orbiting satellite, that means it's awfully close to the surface of the Earth, which means the radius of the distance between the center of the Earth and the low orbiting satellite is pretty close to just the radius of the Earth. Okay, and if we think about the force of gravity when you're close to the surface of the Earth is just mg, but by Newton's second law, that equals the acceleration in the radial direction, the centrifugal acceleration, but we know that that equals the tangential velocity squared over the radius. Okay. Then we can set this equal to this, and we end up with g equals vt squared over r, or vt equals square root of g times r, which is what we had before. Okay, so this came from using our definition of force of gravity, it being the only force acting, so it's the net force, pointing in the radial direction, and our radial acceleration has its special relationship with the tangential speed. Okay, so backing up then, let's look at this problem. We are not given the mass of the planet, and we don't know its g constant. What we're given is the total gravitational force. So we can still say this. We can't say this equals mg, but we can say that this fg equals mass of the moon, its velocity squared over its radius of orbit, its orbital radius. And this is given. Okay, the mass is given, and this force is given. Okay, so we can find this v a little bit differently now. It's rfg divided by m, and that's all square rooted. Okay. Now just to see how it's the same, if that was on the Earth and close to the surface of the Earth, then that's just mg, and the m's cancel. We're left with this relationship. Okay, but knowing where it came from allowed us to find this for this different problem. Okay, and so we can plug that in, and we can end up with that being 418 meters per second. Okay. And then the problem asks for the period, the orbital period in terms of Earth days. And so that's just a definition of velocity equals distance over time, or circumference over period is the same thing, because it goes in one period, it goes one circumference. And so that equals 2 pi r over t. So solving for t, going to be 2 pi r over this velocity. If you do that, you're going to get about 26 days, converting it to days. Okay. And just as a reference, the period of the moon around the Earth is 27.3 days, and so it's not too crazy different there. And if you look at the table of values in the back cover of your book for the moon and its radius, and you can calculate the force between the moon and the Earth. You can see that it's similar values, but different enough. And we've got these relatively similar values. So that is the activity for today. So if you have additional questions, feel free to email me, set up an office hour, or come to our class time if you're able to make that.